I welcome you again to the UNU-INWEH public event, the Science Talk. For those joining us for the first time, I say a warm welcome to you. We are glad you can join us today. Thank you. I am your host, Professor Grace Oluwatonya. Before presenting our distinguished speaker for this morning, please note that there will be an interactive Q&A session at the end of the presentation. At that point, there will be room for comments, Q&A, and any other contributions. Please type your questions or comments in the Q&A chat box, and we will pick them up from there afterwards. Thank you. The topic of today's talk is Transdisciplinary Approach Toward Climate Resilient and Equitable Infrastructure. So, let's talk. Our presenter is Professor Farshid Vahedifard. I hope I got that correctly.
Yes, you did.
Fantastic. Professor Farshid is the lead Resilient and Equitable Infrastructure at UNU-INWEH here. He's also a professor and Louis Berger Chair at the Department of Civil and Environmental Engineering, Tufts University, United States of America. His research efforts cover civil and geotechnical engineering, interfacing with the grand challenges of climate change, resilient infrastructure, and environmental justice. He has led several transdisciplinary research initiatives on emerging issues related to climate resilient communities and infrastructure systems, aging infrastructure, extreme events, cascading hazards, inclusive adaptation, and environmental justice and equity. He has received over $8 million of research grants as a principal investigator, and in total about $26 million from various sources, and he has authored over 200 peer-reviewed articles, including supervision of over 50 postdocs and postgraduate students. Very impressive. He is a fellow of the American Society of Civil Engineers and a recipient of several awards, among which is the Normal Medal, MSU Annual Research Award, the Federal Laboratory Consortium Interagency Partnership Award, among others. So, join me in welcoming Professor Farshid to this morning's talk. Professor Farshid, you are welcome. Over to you.
Thank you, Grace, for the warm welcome. Good morning, or I guess good afternoon, depends on where you are attending this presentation. It's a pleasure to be here and give this presentation. The idea is to give an overview of our research approach on how we can address some issues related to climate resiliency and equity in a changing climate. The first question is, why do we need to care about resilient and equitable infrastructure? I thought to start the presentation with a case study that just happened recently. Back in March 2023, there was a flood in California, which, as you can see on this picture, flooded a town called Pajero and led to failure of a levee. Levee is an earthen embankment which is used as flood protection infrastructure. The levee failed, the whole town was flooded, several people were killed, and there were several issues related to levee failures and flooding. People lost their electricity, they lost access to their the grocery and other critical infrastructure sectors at that area. We have been working on that area for a while, and we know that California has experiencing several climatic trends, including drought, severe drought, multi-year drought, followed by extreme wet year. And levee system in that area are relatively old, and they're not prepared for this evolving patterns of climatic change. So, but the thing is, I was talking to a reporter from Los Angeles Times, and she asked me about the issues with levee systems in the area. And I explained there are several technical problems. We knew that the levees were not in good shape, and we are dealing with unprecedented rainfalls in the area, which happening after multi-year drought seasons. So a combination of climatic drivers are impacting levee systems. So the levee system were performing under marginal conditions, and now we are dealing with unprecedented flood, causing those levees to fail. At the same time, I suggested her to look into the communities living behind those levees, and I told her that there are a large percentage of disadvantaged population living in the area. She looked into them, and then she realized that she could talk to somebody from Army Corps of Engineers, and they admitted that they knew that the levee would fail, but they did not take any action before because they thought it's not worth it. Because that area is a very poor community. They don't even have like a post office. And because of that, they did not take any action. And that's what they said. It's a low income area. It's largely farm workers that live in the town of Pajero. And therefore, you get basically Bay Area construction costs, but the value of property is not at all that high. That was the point that I was trying to make. And I told the reporter that, this is an example where we have historic issue with infrastructure equity. And as you can see in this case, what did we have here? As you can think about it, we had a triangle of climate change impact on extreme events, marginal infrastructure, and disadvantaged population. And these three components can turn a natural hazard to a human disaster. And that's why we need to plan for resilient infrastructure. At the same time, we have to prioritize equity in our infrastructure planning. And why do we need to do that? Because we know that there have been historic issues with investment, planning, maintenance of infrastructure, particularly in disadvantaged population. Why? Because they typically deal with marginal infrastructure, because typically their voice is not incorporated into planning and financial assistance in infrastructure. That's why they're paying higher costs of climate change as we deal with more frequent and more severe events. And that's why in most cases we see those people who have had the least contribution to excessive CO2 emission and to the trend of climate change, they're paying the highest cost for climate change. That requires us to work together to address issues of climate change for our infrastructure while trying to address some of historic issues and systematic issues in terms of infrastructure equity. And here you see the numbers in terms of the number of billion-dollar extreme weather events in the United States. So as you can see, despite all the investments that we have made in our infrastructure to become more resistant and resilient against extreme weather events, we see an increasing trend in the number of billion-dollar disasters. We just had multiple hurricanes. We had several fires affecting the area. As you can see, we are dealing with a rising number of billion-dollar disasters. At the same time, we see in several cases that disadvantaged communities, disadvantaged populations are disproportionately affected by those extreme events and natural hazards. And this graph, since this is related to the scope of this presentation, shows the number of billion-dollar flood events happening in the United States. The same thing you see at the same kind of extreme flood events happening more and more frequent and causing more and more billion-dollar events or losses to communities in the United States. Part of that is because of land use, land cover changes, urbanization, population growth in certain areas. But a good portion of that is due to anthropogenic climate change, which has led to an increase in the number of billion-dollar disasters. So we know the problem. So what's the solution? How can we address this issue? This problem is a multidimensional problem by nature. It requires us to go outside our comfort zone, work together in a transdisciplinary framework to make sure we can address several aspects of this problem. Yes, we have a very strong engineering science component to quantify how climate change impact the patterns of extreme weather events, to quantify the impact of those climate-adjusted extremes on our infrastructure, but also to better understand communities shortfall in information, better understand communities' needs, priorities. Different communities, they have different adaptive capacity. They have different risk threshold. We have to consider those differences in our adaptation strategies. And that's why we need to work together in a transdisciplinary framework to address issues related to climate resilient and equitable infrastructure. In this presentation, I want to show an example of such framework that we have established over the past several years, working with several colleagues. The work that I'm presenting today is a result of a collaborative work with several of my colleagues. I have to acknowledge their contribution in this presentation, and also several of my graduate students and postdoc work on this project. So I have to thank them and acknowledge their contribution. What are we going to talk about today? We are going to talk about levees in a changing climate. Levees are the primary flood protection infrastructure in the United States and several countries like Netherlands, China, and several other countries. Most of those levees were built several decades ago, even a few centuries ago, using by farmers or settlers. So they don't have rigorous engineering design or construction. That's why I like to call them semi-engineered structures. Over the time, because of urbanization, because of land use, land cover changes, all of a sudden they become a critical component of our infrastructure system. Now they're playing an unintentional critical role that they were not prepared for. Now we are dealing with more extreme and more frequent flooding, which makes things even worse. Aging levee systems are exposed to more frequent and more severe flooding system, which can make them more vulnerable. The goal is basically what are we trying to do? We are trying to enhance the resiliency of levee system in a changing climate and develop adaptation strategies that can answer climate resiliency of those levee systems while integrate equity and justice conservation. So that's the goal of the presentation today. Toward that goal, we have three main objectives. First thing is how climate change is impacting the statistics of flooding in terms of frequency, in terms of intensity of flooding. That's the first objective, the science of flooding in a changing climate. The second part is, okay, once we know the impact of climate change on stressors, which floods in this case, what would be the impact of climate adjusted floods on levee system at the structural level and regional scale? Once we quantify the impact on levee system, let's look at communities, how we can develop solutions, or better to say, how we can co-develop solutions to ensure the resiliency of those levee systems while promoting equity and justice criteria by prioritizing disadvantaged communities that they have lower risk threshold and lower adaptive capacity. So throughout this presentation, I'm going to walk you through those three main objectives. Given the time limit, I'm going to present some of the results for each step, but there will be much more. What I'm presenting is the result of several articles. I'll be happy to share more details on articles if you're interested. Levees, let's look at levees quickly. It's estimated we have over 38,000 miles of levees in the US with an average age of 60 years. So as you can imagine, they're aging and they're old. Over 36 million of people live behind levees. And it's estimated that levee systems are protecting over $2 trillion of properties behind them. In the figure on the bottom left, you see the distribution of levee system. As you can see, they're wildly extended throughout the nation, but they're not in good shape. The latest infrastructure report card gave a grade of D to levee system. Of course, not a great grade to get, and that's not ideal. So what does it mean? We are dealing with marginal infrastructure exposed to more frequent and more severe flooding. With that, we have to understand the risk. The first step to address any risk is risk awareness. To understand the risk of levees in a changing climate, we have to look at different components of risk and see how those components are changing in a changing climate. In general, we can talk about three components for risk: exposure, hazard, and vulnerability. We have to look at each of those components and see how those components are evolving in a changing climate, which will help us to quantify the evolving risk of levees in a changing climate and develop our solutions to address that evolving risk. In terms of hazards, we are dealing with multiple stressors affecting levees. Of course, flood, extreme precipitations, sea level rise, land subsidence, even drought. And in some cases, even non-climatic stressors like animal boring, they're affecting levee system. So we have a combination of climatic and non-climatic stressors affecting levee system. In most cases, it's not just one single climatic driver. It's a combination of climatic drivers and non-climatic driver, the notion that we refer to as cascading and compounding hazards. In terms of vulnerability, we have to consider the effect of aging when we are assessing the vulnerability of levee system. We have to consider different modes of failure because levee systems, as I said, there are embankments, earthen embankments, and they can fail under different modes of failure. We have to consider the interaction between different modes of failure, and we have to consider the impact of climate-adjusted extremes on the vulnerability of those levee systems. In terms of exposure, we have to consider that we have land use and land cover changes and population growth behind levees in several areas. What does it mean? It will increase interdependency between levees, communities, and other infrastructure systems, which will add more complexity to the problem that we are dealing with. That. Uh, for several reasons, disadvantaged communities are more vulnerable to levee failures. Typically, lands behind levee system are cheap lands, so disadvantaged population tend to go and live there because they're cheaper lands and it's easier for them to afford the living expenses down there. Because of that, they have higher exposure to flood and levee failure. Typically, they suffer from lack of resources and socioeconomic barriers and marginal infrastructure in those areas. This figure schematically shows why disadvantaged communities are more vulnerable to the evolving risk of levees in a changing climate. To address this issue in our study, we have proposed a five-step framework. This five-step framework is an iterative framework working with community to identify the risk, co-develop solution, implement the solution, evaluate the solution to make sure we achieve the goal of resiliency and equity, and make refinement as needed. So this is a five-step iterative process. I'm going to show you results of some of the steps throughout the presentation, but please note that there are much more details in each step that can be discussed in separate presentation and discussion. What's the first step? The first step to better learn, better understand our communities. We call it community identification. Identify communities in most need of adaptation. Identify pre-existing barriers in communities. Identify socioeconomic attributes. Identify a levee system in those areas. Identify flood risk on those areas. That's the first step. The second step is, okay, once you did your homework for community assessment, the second step is to develop a two-way relationship with community for community engagement, to better understand their existing practices, to better understand their risk threshold, to better understand their information shortfalls. And this two-way relationship with community is very critical because we want to maintain this two-way relationship throughout the study. It's not just one-way relationship. We go to them and tell them this is the product that we have and you have to implement it. No, that's not going to work. We have to listen to them. They have been dealing with flooding with several decades, several centuries, to understand their existing practices and see if we can improve them, build on their existing practices. That's the second step, community engagement. The third step is to do the science and engineering, to quantify risk of levees in a changing climate. As I said, we have three components: exposure, hazard, vulnerability. Do your engineering part, do the science part, do the climate change modeling part to understand and quantify the evolving risk of levees in a changing climate. That's the third step. After that, once you quantify the extent of the problem, now let's develop or co-develop solution, adaptation strategies. In the fourth step, we will develop a portfolio of adaptation strategies. How can we improve? How can we mitigate the risk of levee failures in a changing climate? We will work with our communities, stakeholders, to develop a portfolio of different adaptation measures that can be possibly used. And then we will use those adaptation measures in a multi-objective, multi-attribute decision-making system to define, to identify optimal adaptation strategies. What do we call by optimal adaptation strategy? Optimal adaptation strategy is a strategy that is technically sound from engineering and science perspective. It's practically feasible And third, equally important, is socially just. So we consider socioeconomic attributes. We consider communities' risk threshold. So those are three main objectives that we have to concurrently address in our multi-objective optimization framework for decision-making process. So in the fourth step, we compile a portfolio of adaptation measures to minimize the levee risk in a changing climate. And then we use them in a multi-attribute decision-making system to identify optimal adaptation strategy, which is technically sound, practically feasible, and socially just. The last step is to implement them and keep monitoring them. Get feedback from communities, end users, and stakeholders to make sure we achieve the goal of resiliency and equity. If needed, make adjustment and refinement in adaptation measures and improve it. So it's an iterative process. Those are 5 steps. Let's look at some more details about each step. First step, identify levee-protected disadvantaged communities. We wanted to do multi-scale screening to understand what communities live behind levees. What are the areas that we have to zoom in and prioritize for adaptation strategies? First step that we did, we took the National Levee Database. National Levee Database is the largest database of levees that I just showed a picture a few slides ago. And you see the distribution of levees and areas protected by levees. We look at socioeconomic composition of people living behind the levees and compare that to communities living in non-levied areas. So when I say levied areas refer to the area protected by a levee system. Non-levied areas are the areas that they don't have a levee system in place, so they don't need a levee system in place. And look at the composition in terms of socio-demographic composition of levied area. Interestingly, we look at state level, we look at regional level, we look at national level, and interestingly, we saw several disparities in terms of overrepresentation of historically underserved and socially vulnerable communities behind levees. Let's look at, for example, white population, shown by blue color in this figure. As you can see in this figure, nationwide, we have 54% of white population living behind levees, but in non-levied area, we have about 65%. So you see overrepresentation of white population in non-levied area. But for example, for Black population, we have more Black population behind levees area. The same thing for Hispanic population. In several regions, we have Hispanic population overrepresented behind levees area. So it shows that we have this disparity. We look at disparity percentage in terms of several other socioeconomic attributes. And what we did, basically, we calculated an index. We call it disparity percentage. Disparity percentage was the percentage of that vulnerable population in levied area compared to that population in non-levied area. And that's the relative difference. So if you have no disparity, that disparity index would be 0. But see, in several regions, we have large disparities. As you can see, of course, people with low education, with poverty, are overrepresented behind levees. Also, as if you see with, for example, Hispanic or Latino, they're overrepresented in several areas. For Black population in some regions like Southeast or Midwest, we have Black populations overrepresented behind levees area. What does it mean? It means that we have disparity in terms of race, in terms of ethnicity, and in terms of other socioeconomic factors. This table summarizes the disparity percentages for different factors. As you can see, nationwide, we have 40% disparity in terms of Hispanic population. What does it mean? Hispanic population are 40% overrepresented behind levees compared to non-levied areas. Or in terms of poverty, poor population are 20% overrepresented behind levees at the national level. You see disparity percentages for regional levels as well. I don't want to get into the details. For socioeconomic attributes, we did the same thing at regional scale. The spider plot on the top right shows the number of states that they have disparity. As you can see, for example, for poverty, disability, low education, we have more than 40 states out of 50 states having disparity. It shows the extent of the problem. For example, for Hispanic population, we have more than 30 states with disparity in overrepresentation of Hispanic or Latino population behind levees and so forth. You see the results for different states. So we did the analysis at different states. So, so we quantify the disparity, and then the last index that we look at is an index called disadvantaged community designation. This index was recently developed after White House Justice for the Initiative. They consider several indices like social vulnerability index and several other indices, and consider different factors like climate change, housing, energy, health, and to identify if a census tract is designated as disadvantaged or not. If they don't meet certain criteria, that census tract will be designated as a disadvantaged census tract. So we'll look at communities behind levees to see what's the percentage of disadvantaged population living behind levees. Not surprisingly, we noticed that at the national level, we have 40% overrepresentation of disadvantaged population living behind levees. You see disparity percentage, state level, in the map and regional level at the bar chart on the bottom right. And you can see that in several areas, even disparity percentage is more than that 40% national level. That gives us an idea about the extent of the problem and where we have to zoom in to develop and prioritize for adaptation strategies. This figure shows population behind all levees and also population behind levees that are accredited with FEMA and non-accredited with FEMA. If levee system is not in good shape, FEMA won't give accreditation to that levee system. So, but we consider all different levees. Results are pretty much the same and similar. Also, we'll look at levees with different risk classification in terms of high risk, medium risk, and low risk levee system. Unfortunately, I have to say that levees with high risk or moderate risk, they have very high percentage of disadvantaged community living behind levee system. For example, at the national level, we have 57% overrepresentation of disadvantaged population living behind high risk levees. And 57% overrepresentation means that they are significantly exposed to levee failure risk. For moderate risk, we have 76% overrepresentation of the disadvantaged population. So it shows you a very clear picture of the extent of the problem. After doing so, we wanted to see, okay, we know the extent of the problem. So what should we do? We need to develop we need to inform some action items. For doing so, we adopted this priority matrix, basically, which is urgency importance matrix developed earlier. And in this work, we also collaborated with our colleagues. Professor Madani also contributed to this work. We adopted this matrix. What's the idea? The idea is to quantify both resiliency and kind of equity consideration in one graph to identify which areas we have to focus on. Why do we do that? Because no matter how much funding you have, at the end of the day, it will be limited resources compared to the extent of the problem. It brings up the question is, where should we prioritize? How should we prioritize? This priority matrix is supposed to inform us about prioritization. So as you can see, we have two indices here. On the y-axis, we have disparity percentage. As I explained, disparity percentage shows the percentage of vulnerable population behind levee compared to percentage of vulnerable population in non-levied areas. That's the relative change. The x-axis index shows levee exposure index. We wanted to capture what's the population living behind that. In some areas, there is a very low density population area, but we wanted to see what's the density of population. So exposure is indexed in that x-axis. So with that, the numbers, the boundaries that you see are defined based on national medians, but you can define those boundaries based on other consideration. Here, we use national medians to define those boundaries. So you have a 2x2 matrix. The points that will fall on the top right quartile are the urgent adaptation. We need to prioritize them for adaptation, for evaluating vulnerability of the levee system under multi-hazard scenarios, and develop a portfolio of adaptation measures. With that in mind, we'll look at different states and we kind of map them on this priority matrix. Let's zoom in to see what we have. This graph shows several sets of data. Again, we talked about the X and Y axes, but the size of each circle shows the population of disadvantaged communities living in that. The larger the circle, the higher the population of disadvantaged population in that. And also, the color shows percentage of basically the disparity percentage. The darker, the worse. So with that chart, we can identify the areas or the states that we have to prioritize. Of course, the states that are falling on top right quartile are the states that we have to prioritize. That's what we did, and that's how we can kind of go after adaptation in those states. Okay, we did this. So we did national level. We use several indices, existing indices. We develop or propose 2 new indices. And using those multi-level screening and spatial analysis, we identify the areas that we can zoom in. The second step is community engagement. There are several different types of community engagements and activities that we are pursuing. I'm just going to keep it limited to some of the methods that we are using here or we are planning to use. But I'm not going to get into the details of those methods. Again, as I said, in the second step, we want to establish two-way relationship, two-way dialogue with communities in those areas that we prioritize. And in those areas, we have to understand what they have been doing, what has been their experience living behind levees, how much they know about the risk living behind levees, and what should they do in the case of levee failure or flooding. And the idea is to develop outreach and education, to develop collaboration, and develop partnership. We propose to identify quality of life indicators for those people living behind levees, and then establish levee adaptation committee to basically identify communities' priorities and communities' needs. With that, I'm going to keep it here and then move to the third part. In the third part, we want to do the science. Quantify the risk of levee failure in a changing climate. As I said, we are dealing with vulnerability, hazard, and exposure. This is the part that you bring in your science and engineering into the consideration. For modeling levees, we use multiple methods, multiple engineering methods. I'm a geotechnical engineer by training, focusing on earthen infrastructure, modeling, soil, and earthen embankments. So this is my core technical area in this work, but I will keep it limited. We use multiple approaches. First, we did field monitoring and model calibration. We selected a site. We had a site that we had a very well-instrumented levee system. As you can see here, this is the graph, and this is the levee section. We had all kind of instrumentation, piezometer to measure pore water pressure, water gauge. We were measuring deflections, and those were used to kind of get a better idea of field scale response of levee to climatic variation when we had rainfall, when we had flood, when we had water fluctuations. Then once we had that field data, we used the field data to develop a physics-based numerical model. We had several input layers. We had climate data. We had hydraulic loading in terms of flooding and precipitation. We had soil properties, mechanical, hydraulic, thermal properties. And we had to consider vegetation impact. We had to consider land climatic interaction model. And we had to consider all these processes in a coupled manner, which means that they interact with each other. We did that, and the output was the stability, the factor of safety and probability of failure of levees under current and projected future climates. And we look at different modes of failure, and the final output was a set of fragility curve. Fragility curves, for those who don't know, are a set of curves that kind of are commonly used for quantitative risk assessment of infrastructure. They represent the probability of failure with the level of stress or level of loading. For example, earthquake magnitude versus the level of collapse or level of damage in buildings. In this case, the level of flooding versus probability of failure of levees. We did that. This is the data that we got from our field monitoring data, and we used them for calibrating our numerical model. We collected several data like pore water pressure from different sensors. We used some advanced calibration procedures, and also employed some machine learning techniques for calibration numerical modeling. We did that, and we developed this numerical model. We consider variability. This is a finite element model of earthen levee. We use historic and projected future flood data, apply that as hydraulic loading condition. We consider the variability in hydraulic and mechanical properties of soil. And then we consider different modes of failure. Undersea page, uplift, and slope stability. As I said, levees can fail under different modes of failure. Using this physics-based model, we could capture 3 of them under current and projected future. But we also need to develop a data-driven model to capture another mode of failure, which is called overtopping. Overtopping is the most dominant mode of failure. To do that, we compile a database of over 230 levee overtopping events, and we develop a logistic regression model to quantify the probability of levee failure due to overtopping. We selected the most significant attributes, and based on that, we had 5 primary attributes controlling probability of levee failure due to overtopping. So we did field monitoring, we did structural scale physics-based modeling, we did data-driven modeling. The last step was to basically, after doing so, to do a regional modeling. Because for regional risk assessment, we wanted to do regional modeling. What did we do? We took the data-driven model that we had. We applied that in a GIS framework for spatial mapping and modeling. And then we used different sources of data, as you can see on this figure on the left column: soil properties, elevation, flood data. And we collected that, and we did a spatial analysis. And using the model that we had, we could create a probability of failure at the regional scale. So that was the last step of our physics-based modeling. Let's look at some of the results quickly. First thing first, my hydroclimatologist colleagues and hydrologist colleagues, Professor Aga Kuchak and his colleagues, they were able to model how basically flood frequency will change in a changing climate. For example, if you look at the graph at the bottom right, you see a heat map of flood water level under past and future scenarios for different flood frequency. For example, for what we know as a 5-year flood, using historic data, flood water level would be 17.5 meter. But under future scenario, that can get up to 19.6 meter of flood water level. You see a significant difference in flood water level, which can have significant impact on probability of failure and factor of safety of levees. We did the same thing for flood discharge versus flood frequency, and we did the same thing for stream flow recurrence intervals versus stream flow. And in all cases, they used different climate models, and they did the analysis their own part to look at the variability and uncertainty. But overall, you can see that considering climate change, we will dealing with more frequent and more severe flooding. So for example, in some area, we saw that a flood that we call it 50-year flood now, it can happen every 25 year, every 30 year. That's the frequency. In terms of intensity, the flood water level increased in several regions. We did that, we incorporated that in our physics-based model, and these are probability of failure of levee system under different modes of failure. This figure shows probability of failure for different modes of failure under current and projected future climate. For example, on the top row, you see the result using projected future flood data, and the black lines show the results using historic flood data. In all cases, you see probability of failure of levees significantly increased if you consider projected future climate data. What does it mean? We need to prepare our levee system to resist against those more frequent flood systems. The results will inform us about the quantification and the quantity of that change. This also shows the probability of failure for different return periods of flooding and lifetime of basically structure. So depends on where you are, depends on your planning purposes, you can quantify the change in probability of failure of the structure for that structural level, basically risk assessment. But we don't want to limit to structural level. We want to do regional scale. As I said, we implemented the model in regional scale, and we consider as a network, and we could quantify probability of levee failure under different flood scenario, under different flood duration, and we use that for planning purposes. With that, let's jump to part 4, when we develop equitable adaptation strategies. And I would like to call it co-develop, because this is something that we have to work with our community partners, stakeholders, local decision makers, to make sure adaptation strategies are addressing their needs, are addressing technical consideration, engineering consideration. Also, they address equity and justice consideration. In terms of adaptation, as I said, we have a multi-attribute decision-making system. We first did community assessment, did community engagement, we quantify flood risk, we develop multi-objective decision support system, and then we develop an intervention portfolio, and then we identify optimal adaptation strategies. The figure on the right shows a sample of adaptive decision-making framework, which is originally proposed by people from Deltares in the Netherlands, but we are adopting a similar approach to show what will happen under different climate scenario, what will happen under different adaptation strategies. What we did recently, this is a very recent work, for the first time, we created a database of different flood adaptation measures. Based on the IPCC recommendation, we grouped them into 4 groups of infrastructural, technological, institutional, behavior, and nature-based adaptation strategies. For each, I'm not going to get into details, but for each adaptation measure, we identify advantages, disadvantages, co-benefits, and trade-offs. Remember, there is no one single prescription that works for all communities. We're going to work with communities to identify advantages, disadvantages, co-benefits, and trade-offs for that particular communities. That's the thing that we are talking about, co-development. We have more than 30 different adaptation measures. For one community, it might worth to spend more on hard adaptation measure. But for another community, we might need to focus more on nature-based solution or behavioral cultural solution. So each community will have their own specific characteristics. So we have to integrate those specific characteristics in our adaptation decision-making. And then we propose a risk-based adaptive design, basically to look at the levee system and consider projected future climate, select a risk threshold based on community risk threshold, do the design based on that risk threshold, and then keep monitoring the structure to see if it can meet the requirement of design. If yes, you're good. If not, you need to make refinement adjustment. This is something that we recently presented in our study and shows how you can quantitative risk climate data and integrate that into analysis and design of levee system. And also it's an iterative system. So basically you keep monitoring and evaluate it based on that. What's the goal of adaptation? When you design adaptation, the first step is to see what's the gap in terms of disadvantage and non-disadvantaged population to levee failure risk. And that's where we developed this chart. On the x-axis, you see probability of flooding. And this probability of flooding is increasing under a changing climate, considering different climate scenario. The y-axis shows the levee resilience index, as an index that is calculated using probability of levee failure that we just calculated. The first step is to use existing levee system and to develop the curves under the current under current condition with no adaptation measures. With doing so, we will create those curves that we call them no adaptation. We will create those curves, but we create the curve for disadvantaged community and non-disadvantaged communities separately. Why? We want to see the disparity. We want to quantify the disparity, and we call this gap equity gap in levee resilience. Once we quantify disparity, the next step is to use our multi-attribute decision-making system to identify optimal adaptation intervention strategies that can satisfy two goals. First, to boost both curves up, to push both curves up, to improve the resiliency of system for both communities. That's the first criteria. At the same time, we want to minimize the gap between the two communities. And as you can see, for those curves showing adaptation action implemented, both curves are going up and there is minimum gap, no gap between the two curves. What does it mean? We kind of improve the resilience of the system across all communities while we minimized or eliminated the gap between different communities. And one thing that I wanted to say, the y-axis is a weighted number. For communities that are disadvantaged, they have low risk threshold, we assign a weight to kind of prioritize them because we want to consider the lower risk threshold and lower adaptive capacity. So that's how we do the adaptation decision making to make sure all communities are better situation in terms of climate resiliency while we are prioritizing disadvantaged community or adaptation decision making. As I said, we want to make sure our adaptation solution is practically feasible, technically sound, and socially just. Here we identify what we mean for each of those considerations. Practically feasible should be cost effective. We should consider environmental constraint. We have to be regulatory compliant. We have to also have technology and experience needed to implement that adaptation strategy. In terms of technically sound, we have to consider changing climate, the science of changing climate. We have to have engineering of changing climate, engineering of designing and maintaining levee system. And we have to make sure our levee system will be safe under multi-hazard conditions. Socially just, as I said, we have to minimize risk disparity, and we have to be inclusive and transparent in decision making. And we have to have equitable resource allocation considering communities' risk threshold and adaptive capacity. And we have to co-design our adaptation strategies with our community partners. This is an iterative process, and we will continue once we implement those adaptation strategies and monitoring strategies. We will keep monitoring them. We will evaluate to make sure we achieve the goal of adaptation. Our community is satisfied with what we did, and we do continuous evaluation of outcomes. We continue monitoring changes in hazard, exposure, and vulnerability, identify shortcomings and gap in adaptation process. So this is basically an iterative process. If needed, we're going to go back and make refinement in our adaptation strategy and then go through the same process. So it's an iterative process. We start from community and we get back to the community. We do the science in the middle. We work with them to co-develop adaptation strategies, implementing them, and then we're going to evaluate them along the way. Just to wrap up, we know that climate change is increasing frequency and intensity of climatic extreme in several regions around the world, and disadvantaged populations are disproportionately being affected by those. Here in this presentation, I wanted to show how we can work with different disciplines in a transdisciplinary framework to address equity and resilience at the same time, to make sure our infrastructure systems are resilient. At the same time, we address equity issues that we have had historically. We apply the framework to levee system, primary flood protection infrastructure system in the United States and several other countries across the world. And this adaptation framework can be applied to other infrastructure systems to other countries. I would like to invite all of you attending this presentation to think about how you can adopt a similar framework in your sector, in your infrastructure system, in your own country, in your own region. It requires all of us to go outside our comfort zone and think outside our regular boundaries. With that, I'm going to wrap up my presentation. I would like to acknowledge our sponsors helping us, supporting our project, National Science Foundation, USDA, UNU-INWEH, and earthen. Thank you. I think I'm a few minutes over time, but I'll be happy to answer if there's any question.
Okay. Thank you, Professor Farshid. It's been an interesting talk, but I'll jump in very quickly. You keep saying we. Can you please break that down? Who are the we? Are you talking about researchers, scientists, or just break it down? Who are the we?
That's a great question. I guess I said we because, as I said at the beginning of the presentation, what I presented today, we have a multidisciplinary team of scientists, engineers, and community partners. That's why I refer that as we, because it's not one discipline or one person that can handle all different components. That's why I call it we, because it's not only research team as well. We had community partners helping us to identify their problems. Sometimes communities have some very smart ideas for flood protection, and they've been using it for decades or centuries. That's why it's very important to listen to them. And that's why I call it we, because when we are co-developing our adaptation strategies, we have to make sure we bring in that indigenous knowledge into our adaptation decision making.
Thank you.
Sure.
But now I will explain why I had to ask that question. When you go into co-development, now referring to researchers and communities, if you do not include those who will do the implementation, because now these are public infrastructures, they're not an infrastructure credited to households or just communal infrastructure. So you still need some good level of political engagement, a good level of government involvement, so that's why I needed you to clarify we. So are those who will implement the actual adaptation strategies included in this process or not? So are you guys just at the current we going to finish all this elaborate work, then start to now kind of secure the buy-in of politicians, those will actually bring in the money? So that's the reason behind that question. So how much influence, how much involvement, let me rephrase that. Do those who will implement actually included in this week?
Great question. In the United States, the levee system, a part of levee system are federal levees that are maintained by the U.S. Army Corps of Engineers. But we also have private levees. Those private levees are the levees that they're not owned or maintained by the Army Corps. So we have both federal and non-federal levee systems. But overall, I would say in the United States, U.S. Army Corps maintains a large percentage of levee systems. And but a few years ago, there was a national initiative to establish a center called National Levee Safety Center. The idea was to get different agencies involved, like NOAA, Army Corps of Engineers, together in a central, basically, afford to kind of better address issues related to levees. In a couple of our projects, I've been working with that National Levee Safety Program to kind of to get their feedback and to develop those solutions. One thing that I wanted to say, when we are talking about adaptation strategies, the first thing that people typically think is we are talking about building higher levees or like making new levee systems. Those are hard adaptation, but adaptation strategies can be pretty wide in the range of activities that we can do. As I said, the first step for addressing any risk is risk awareness. Sometimes developing community engagement activities to enhance the awareness of communities about the risk of living behind levees, or what's the status of levees that they live behind. Doing some outreach activities or some community engagement activities can be informal education. That can be also part of like a adaptation. That's what we call it, adaptation strategies. But back to your question, in some parts of our work, we had those decision makers that you're talking about involved in the project. One of the projects supported by National Science Foundation, we have National Levee Safety Program as our partner and sponsor in the project. So,
okay, thank you. But who initiated this? The scientists or decision makers?
sorry, I didn't get the question.
I just want to know who initiated the initiative, the project and all. You know, is it initiated from the academic angle, or it was initiated based, you know, is it a need-based initiation? You know, I just wanted to know.
A very important point. Very important point. We had several scientific questions that we wanted to address, but even during the development of the project, we work with our partners from like practitioners, like decision makers, to better identify the problem that will address their needs. Okay. So it was a combination of our academic questions and their practical needs. That's why we had several meetings, several conversations, even before putting together our proposal. That's something that we are trying to do. And one thing related to what I just presented is there have been several initiatives in the US. One of them is infrastructure law. The other one is Inflation Reduction Act. All those federal investments are promoting or they are intended basically to enhance the resiliency of infrastructure system in a changing climate. They also have a strong emphasis on equity and prioritizing disadvantaged population. But all federal agencies, one thing that kind of has been said by all federal agencies, we need practical framework to tell us how to do it, how we can promote resiliency and equity at the same time. That's what we are trying to do. We are trying to provide a practical framework that they can address both resiliency and equity at the same time. So I would say it's a need based on several recent federal investment in this area and the conversation that we had with stakeholders and decision makers. At the same time, several research questions that we need to address.
Thank you for that clarification, and I appreciate the fact that the framework, is adaptable and is scalable, at every, it can be tailored to specific context. Yes, you made it with this case study, piloted case study in mind, but I can see that it's actually usable, everywhere. And I guess that would be one of the takeaways for me. Yes, I have a director who keeps saying the issue of equity is not only restricted to low and middle income countries, that we have a lot of issues in affluent nations as well that need to be spotted. So I appreciate the development of this kind of framework that can help practitioners, across the globe, that they can apply it to their local specificity, and they'll get a brilliant result. So on that, I will say a big thank you for sharing the insight, of your work with us. And hopefully very soon, again, we'll get a chance to see more of what we're doing, on these coupling climate change, infrastructure, and equitability in one umbrella. That's quite brilliant. That's quite great. So on that note, if there are no other questions, I'll say thank you to Professor Farshid. Nice to see you, and wish you all the best in American election that is just around the corner. Thank you.
Thank you so much, Grace. And thank you all for attending this presentation. It was a pleasure to talk to you about our work. As you correctly noted, Grace, the framework is scalable and transferable. We're applying the same framework to other problems. For example, recently we started working to apply the same framework to the issue of coastal erosion and coastal resiliency. And working with the tribes and indigenous communities. The same framework can be applied to other stressors, other infrastructure systems. So the whole idea is how we can work community and bringing science and engineering together to address climate resilience and equity at the same time.
Great. All right. Thank you. On that note, it comes to the end of this science talk. See you next week. Thanks.